Welcome, everybody, and thanks for joining us for today's Southwestern Physics and Astronomy lecture. Today we get a chance to take a trip further out into our solar system and look at what are the habitability chances of icy worlds such as Jupiter's moon Europa. And to guide us on that voyage, we're joined by a senior group lead at Southwest Research Institute and a composition working group co-chair of for NASA's Europa Clipper mission, Dr. Tracy Becker. Dr. Becker comes to us from Southwest Research Institute in San Antonio, where she has done research studying both asteroids, Saturn's rings, and now Jupiter's moons as she prepares for the Europa Clipper mission to be launched in the coming years. And without further ado, Dr. Tracy Becker.
Hi, everyone. Thank you. It's great to be here. Thank you for that introduction. I hope everyone is doing well in these very difficult times. And I'm really happy to be here virtually, though I am sad to have not been able to meet you all in person. Like was just said, I'm Tracy Becker. I'm a planetary scientist at the Southwest Research Institute in San Antonio, Texas. And I am part of the NASA's Europa Clipper mission. And I'm really excited to tell you a little bit about that mission today. From my talk, you can see Ocean Worlds, NASA's Europa Clipper mission, and the search for habitability beyond Earth. For more information, there's websites. You can just Google Europa Clipper, and you can find lots of information about this mission. It's a very exciting time to be working on such a mission. So if we can go to the next slide. Okay, so we start our journey at Jupiter. So this is an incredible image of Jupiter from NASA's Juno mission, which is currently in orbit around Jupiter. For this mission, though, that mission is focused on studying Jupiter and producing some of these incredible images. And you can actually follow along with that mission now because it is currently operating there. If you go to the next slide, what we're going to focus on is Jupiter's set of moons that it has. So Jupiter hosts a number of moons. You can see this video here if it streams through quickly enough. Io, Europa, Ganymede, and Callisto are some of the moons you may have heard of already. But those are just a few of a much bigger system of many dozens of moons in orbit around Jupiter. It's almost like its own little solar system out there. But like I said, our focus this talk is going to start with the Galilean satellites. So this is Io, Europa, Ganymede, and Callisto. And if we go to the next slide, the reason that they're called the Galilean satellites might come naturally to you. It's because Galileo was the first one to systematically observe these moons. And importantly, if you're interested in history, these are the observations that actually showed for the first time conclusively that objects in our solar system don't all orbit around the Earth. Maybe you know a few people that think everything revolves around them. At the time, the concept that most people abided by was that the universe was revolving around us, around the Earth. And even though there were certainly scientists who had come up with the heliocentric model where the sun was at the center of at least our solar system, there was no concrete evidence to prove otherwise at that time. They could work out some mathematical ways to explain some of the trajectories of everything in our sky, keeping the Earth in the center. But what's really amazing is you can actually see with a decent pair of binoculars or a fairly good telescope, you can see essentially what's in that image right to the right. You can actually see Jupiter and its 4 moons. They look like kind of just points of light typically from a telescope or binoculars, but you can actually see exactly what Galileo saw. And if you were to go out over multiple nights, you'd see those moons orbit around Jupiter. Galileo, of course, for saying this and proving that the Earth wasn't the center of the universe, was heresy, and he was sentenced to a lifetime of house arrest. But at least we learned a little bit more about the Galilean satellites. Next slide. So the one we're going to focus on for this talk, of course, is Europa. If you go click one more time. Let's see. Yep, Europa. And there's a good reason for that. So if you go to the next slide. We get there. Yes. So NASA's newest, biggest kind of flagship mission to the outer solar system is called Europa Clipper. And this is a mission that's going to go to Europa. It's going to do multiple flybys of Europa while orbiting Jupiter, and I'll talk a little bit later about why that is. But it is considered to be a journey to an ocean world. And if you go to the next slide, I think it's really important, since especially this is for university. I think it's important to question the whats and the whys of what this mission is about and why we're opting to go to Europa. So we'll start first with the assumption that it is an ocean world. So why would we be interested in an ocean world? And I'd love to have the interaction to ask you to shout it out loud, but so you can shout it at your computer screen. I'm sure most of you probably know the answer anyway, perhaps from the title of this talk. But the reason to be interested in ocean world is, of course, and if you click to the next slide, not surprisingly, the answer is life. When we see water in the solar system, we think life because when we see water on Earth, we see life. Even in the darkest depths of our oceans, places where we didn't think life could exist, we often still end up seeing life. And so when we spot large bodies of water in the solar system, we want to know if those could harbor the conditions for life. And especially we want to know if it's current, but even in the past, if it could have harbored life in the past as well. Because I think one of the biggest questions that we have that sort of spans across generations, time, the globe, cultures, everything, that question of whether or not we're alone in the universe is sort of a fundamental question that a lot of people have. And so not only does that make this mission that much more exciting, but it really does get to the heart of a question about our own humanity and our own interests. So if we go to the next slide. So again, before we jump into Europa, the purpose of the Europa Clipper mission itself is to assess the habitability of Europa. And I want to be clear about that. We're not, the mission is not designed to go and say there is or there isn't life. And we'll go through the steps of what this means for the habitability. But the goal is to understand whether or not Europa possesses, or maybe in the past possessed, the conditions that are good for life to potentially exist on that moon. Next slide. So I said it earlier, and I think that this is very important to understand, is what we want to do is talk about going through what we know about Europa and how we know it. So I've told you Europa is an ocean world, but how do we know that? What evidence do we have that this is the case? So to start with, we'll go with some of the basic information. So Europa has a very high albedo, which means it's very, very bright. It's very, very reflective, just visible, natural light. It reflects a lot of sunlight. So that already kind of gives the sentiment of, you know, a reflection that you'd see maybe off of ice, a sheet of ice somewhere, or snow is very reflective. So already, okay, interesting that it's bright. And then we did spectral observations of Europa using Hubble, using past telescopes, past space-based telescopes, current ground-based telescopes, and a couple of spacecrafts that have flown by Europa at this point. And what we did was what we call spectral observation. So this is, you know, basically looking at Europa through a prism. What we are doing is separating the light out and trying to understand Europa at different energies of light or different wavelengths of light. And in the plot that I have on the bottom corner there, that actually shows the spectrum of Europa compared with a spectrum of water ice. And you can see that they're fairly similar. And it's important that they're not the exact same. But the fact that they're fairly similar is really important for us understanding what the surface composition of Europa might be. So it already indicates that there probably is, or a lot, if not all, water ice on Europa's surface. Just because, again, these spectral signatures, they're very, the spectral signatures that we see are fingerprints of the species on the surface. So that's important to remember. Another key piece of evidence that was interesting was that when we did fly by Europa, in the early days with Pioneer, with any spacecraft that we've flown past Europa, we were surprised to see that there were very few craters, basically indicating that the surface is very young. There's no reason that Europa would have fewer craters or be hit less often by asteroids and other material in space than the other moons around Jupiter, like Ganymede and Callisto. In the case of the Earth, we don't have very many craters. And the reason is because we have resurfacing processes happening all the time. We have oceans and tides, we have plate tectonics. These kinds of processes actually refresh the surface, making our surface young as well. So the fact that there's a young surface also indicated that there must be some way to resurface the surface of Europa. Next slide. There we go. Okay, so that's nice. It's nice that we can say, all right, the surface is smooth and it's young and it's bright, so maybe it looks kind of icy. But how does that tell us that there's actually an ocean currently inside of Europa? That evidence came from the Galileo spacecraft that flew in the Jupiter system in the 90s. What happened was Jupiter has a very strong magnetic field, and when Galileo flew past Europa, it noticed a bend in that magnetic field. It noticed basically that Europa had an induced magnetic moment that was interrupting the magnetic field of Jupiter. And the only way you can get that is if you have some sort of conductive material, a conductive liquid material inside, generating that resistance to the magnetic field. And so this is important because it can't just be liquid, it has to be conductive. And so that actually gives you the idea that it's probably a salty water ocean on the inside. There's other reasons for this assumption, for this prediction as well. In fact, just before some of the spacecrafts got to the Jupiter system, there was a mathematical prediction that said the tides from Jupiter, how it affected the moon, would be very similar to the way that the Earth and the moon's tides affect each other. But that the tides were so strong between Jupiter and the other moons in the solar system, tugging on the other moons in Jupiter's system, tugging on each other, tugging on Europa, and tugging on a smaller moon, a larger moon, Io, the closer in moon to Jupiter. Tugging on these moons can actually cause enough friction to keep the inside liquid. The image that you see on the right is actually an image of Io from the New Horizons spacecraft that flew to Pluto. On its way, it passed by Jupiter, and it took this image, and that's an active volcano at the North Pole of Io that you can see in that image. So the prediction was there, and then when we got there with different spacecrafts, we saw that there was, in fact, not only some sort of liquid inside of Io, that it was spewing out volcanoes of basically sulfur material. So theoretically, we knew it was possible. Io, we confirmed it when we got there. And then Europa, again, this evidence showed us that there was probably some sort of salty liquid water underneath the surface, though we have not definitively imaged any kind of plumes on Io the way like we have on Io yet with Europa, although I will talk a lot about plumes on Europa. Next slide. So once we've found this evidence for this liquid water ocean, what else do we know about it? Basically, this is sort of the diagram of what we think Europa looks like on the inside. We believe that the water layer is from about 80 to 170 kilometers below the surface. Then you get the rocky layer, and then you get a metallic core. We estimate that there is twice as much liquid in Europa's oceans than all of Earth's oceans combined. So there is way more water on Enceladus than there is on all of the Earth. And so this makes it even more intriguing as a destination to go to with the spacecraft. Next slide. So next step was not just to see the use the magnetic field and take these very distant observations of the spectra. We want to see what the surface looks like up close. So this is actually an image of Europa's surface from Galileo, showing some of the crazy features that are on the surface. There are these regions we call chaos regions. There are these lineae features that look like they're reminiscent, at least, of possible regions where, like on Earth, when you have two plates, when the plate tectonics and the plates are actually separating. So there's some thought that perhaps some of these lines are actually regions where the ice shell is separating, and the dark red bands are the color of the material that comes up from underneath and sort of fills in and freezes as soon as it reaches the surface of Europa. And so this is one idea of how perhaps we are keeping that surface looking fairly fresh without craters. But it also tells us these discolorations tell us that just saying water isn't the whole story, right? There's some sort of salty material. There's some sort of other materials mixed in with the water ice on Europa. Next slide. Oops, one back. Yeah, so this one, I just love this image. This is showing some of these linear features. This thing is extending for 1,400 kilometers. It's 20 kilometers high. I think that's something like somewhere between 10 and 15 miles high, 20 miles wide, sorry, and a few meters high. So these things are huge. And they're all over Europa. And so getting a closer look at these and understanding how they connect with the other geology and how they connect with the composition of the surface is really key for us understanding exactly what's causing these features and what we can learn potentially about the water underneath by looking at these features closer. Next slide. And so I mentioned water plumes, and I'm going to come to this topic just because it's close to my heart at the moment. On Europa, we have seen several cases of evidence that have shown us that there could very well be water plumes on the surface, coming out of the surface, erupting. And when I say plumes, I'm talking about like a geyser, like water geysers, water volcanoes erupting out of Europa. And the first line of evidence for these plumes came from the Hubble Space Telescope by a group actually here at the Southwest Research Institute. And what they did was they observed Hubble and they noticed emissions of hydrogen and oxygen. And when I say emissions, I'm talking about basically like the aurora, the northern lights that we could see on Earth. These are emissions. These are energized molecules that then are releasing energy and lighting up basically in the darkness of the sky. And Hubble was able to observe these in the ultraviolet, and they corresponded with each other in the exact right ratio to indicate water. So again, this isn't viewing a physical, actual plume yet, but this was very, very strong evidence for the existence of some sort of water eruptions from Europa. Next slide. Then we got some more evidence. The next technique that was used to try to detect these plumes was, again, with the Hubble Space Telescope, but it was to observe Europa as it passed in front of Jupiter. I'm pretty sure in this cool little video that's Io and not Europa, but it's such a cool video and it demonstrates the point, so I still wanted to use it. So what they did was they let Jupiter kind of backlight the moon, and then they looked for any little kind of blips that were absorbing the light coming off of Jupiter, so that you could actually see that backlit shadow, essentially, of the plume. And it worked. They detected some plumes with this technique, both in 2014 and in 2016. But this is really, really, really pushing Hubble to its limits. These are certainly convincing and exciting, but they're not the definitive image of a plume that we really, really want to have. Next slide. The third way we understood that plumes probably could be on Europa, and we're hoping that they're there, and I'll talk about why in a minute, But we think that plumes are there as well because there was actually this really interesting conversation where we were mapping out where these plumes might be on Europa. And there was always this one kind of weird flyby that happened when Galileo was at Europa, where they didn't quite understand the data that came from the particles and the plasma and the magnetometer instruments on Europa or on Galileo. And when they flew by Europa over this one spot, they just sort of had this weird data. They were like, maybe something happened with the data. We don't really get it. They went back with better computational techniques that they have now. And these scientists went back and actually looked at that data again and were able to model it and show that anomalous signal actually is indicative of an eruption of a water plume. So we have these three very different lines of evidence of why we think there are plumes on Europa. Next slide. The last thing I'll say about water plumes, because maybe you're like, well, it's kind of crazy. I already showed you the image of Io, but there's also there's a precedent for this in our solar system as well. The Cassini spacecraft orbited Saturn for since 2004 until 2017, and it detected water plumes off of the Saturn's small moon Enceladus. And so these are actual images from the Cassini spacecraft of these plumes emanating from the surface of Enceladus. So this is definitely something that we've seen in the solar system before. And so that certainly means that it's doable at another moon. Enceladus and Europa are fairly different. However, Europa is much more massive, and so its gravity is a little bit stronger. And so the plumes are, you need a lot more energy for the plumes to go as high as they do off of Enceladus. So that makes them a little bit harder to detect if they're there. Next slide. Awesome. So that brings us to the mission itself. Again, this NASA Clipper, Europa Clipper mission is to assess the habitability of Europa. And we want to do that using sort of four main concepts. We want to understand the ice shell and the ocean. We want to understand the composition of both the surface, the atmosphere, the environment of Europa, the geology of Europa, and search for those plumes, the current activity. And one thing I'll say is you should note the array of expertise needed. When I said earlier, it's a flagship mission. This mission requires a lot of expertise from a lot of different areas of science. We need geologists, we need spectroscopists, we need astrobiologists. We have some of the world's experts from all over the world, all over the U.S., working on this and working together with 9 instruments that we hope to assess ultimately the habitability of Europa. Next slide. And then if you click again, we'll get a little cartoon. This mission is will be about 3 years to start with, and it's going to be at least 45 probably flybys of Europa. So the spacecraft will be orbiting Jupiter and then making these couple-hour passes of Europa, and then going back out to Jupiter, well past Jupiter, and then come back around, swing around, and swing by Europa again. Next slide. I think I talk about why here. Yes. So why? Why not just orbit Europa? We'd get a lot more data if we just could hang around Europa for a really long time and map it all out really, really carefully. The problem is that Jupiter has an extremely powerful magnetic field, and it causes an extreme radiation environment. So basically, the spacecraft and its electrical components and all the parts for all the instruments cannot survive for a very long time in that radiation environment. So the goal is to swing in to see Europa, which is kind of in the heart of that really intense magnetic radiation region, swing by and come back out. And this is sort of the same way that Juno is currently operating around Jupiter. Juno flies over the poles, but swings way out beyond Jupiter, comes in for a close pass, and then goes way back out again. And so we're following that same technique with the Europa Clipper. Yeah, next slide. And if you click again, this is a movie. So one of the goals, like I said, is to understand the ice shell and the ocean. So we believe that the the depth of the ice is maybe a few kilometers, but we don't know exactly. And so we have instruments. The radar instrument in particular is going to help us understand just how deep this water layer goes. We need to understand the salinity of the ocean. So that's where that magnetometer and our particle instruments come into play. So we want to understand, again, how salty that ocean is, and that will actually affect that induced magnetic field again at Europa. So the same way I described how the ocean was detected at all, we can actually use that technique to understand how salty the ocean is. And we also want to understand the surface ice-ocean exchange. So again, this was how much of the ocean is actually coming up to the surface, and how much can we learn about that interior ocean by studying the surface. Next slide. And then there's the composition of Europa. So we want to identify and map the surface. And I've mentioned a couple times now that we don't think it's just pure water ice. There's other components in there, and we want to know what those non-icy components are, especially the organics or the carbon-based materials.
Nice. Thanks.
I think there's an open mic. If we could mute that mic. Okay. We want to study the surface and the atmosphere and understand what those compositions are. Again, because there might be exchange of the subsurface materials onto the surface, so we can learn a little bit more about the ocean. And also some of that material might be in the atmosphere, especially if it goes on the surface and then is sputtered by micrometeorites and other materials hitting the surface of Europa and lofting some of that material into the atmosphere. So we can actually learn a lot about the subsurface, the main surface, and the atmosphere using by studying this composition of all three of those things. It also tells us about other processing. So that really intense magnetic field and that intense radiation environment actually affects the surface, affects the composition of the materials. It breaks it down just like it would break any, our own DNA down if we were standing in that radiation environment. And we actually get some really interesting features on Europa as a result of other things going on in the environment. I showed you earlier that image of the sulfur plume coming out of Io, that sulfuric volcano. That material actually gets swept up by Jupiter's magnetic field and smashed onto the backside of Europa, causing a very different coloration and darkness to one of the sides of Europa. So you actually get a ton of information about what else is going on in the Jupiter system by studying just one moon at a time. Next slide. And one of the other important things is to see this geology in high resolution. So this image was fantastic from Galileo, but think how much our cameras have come since the 1990s. Think about the camera you have in your pocket right now on your phone compared to what the cameras looked like in the 1990s. So the imaging quality that we're going to get is going to be fantastic. And again, we're going to be doing so many flybys, 40 something, maybe even 50 something flybys of this moon, with these really, really powerful cameras, really powerful different instruments. Again, for example, we're going to look at it with the ultraviolet. We're going to look at it in the infrared. So it's not even just a visible camera. We're going to learn so much about the geology and see these sort of different features that are on the surface. And again, try to connect these with what's going on with Europa. How is that surface changing? Why is it changing? And maybe even relate it back to the Earth and see what kinds of processes are happening on Europa that also happen on Earth now or happened in Earth's past. Next slide. And one thing I didn't mention, actually, I'll come back to it. So I did mention the search for activity, and this is again for the plumes. One of the really cool concepts that we can do, if there are plumes coming from Europa while we're there, we can fly through those plumes. And we have instruments that are basically sniffers and tasters of materials. So things that can actually sample the gases and sample the dust and tell us exactly what they're made out of. And so if these plumes are coming from the ocean, we'll actually be able to really understand what the ocean is comprised of by having this direct connection with it. Even if the plumes are emanating from somewhere higher up and not fully down to the deep ocean, that still will tell us a lot about what going on Europa. And again, if there's a puddle of water somewhere in the ice instead of a whole ocean where these plumes are emanating from, that still doesn't preclude the possibility of it being habitable. So the UV instrument on board is the one that I work on. That one's considered the plume hunter because it's the same technique that they were originally discovered with Hubble. And then again, there's a mass spectrometer that's actually being built right here in San Antonio at the Southwest Research Institute, as well as the UV instrument. And that one is the one that can actually sample the gas. And then again, there's the dust collector is being built in Colorado. Next slide. And one thing I did mean to say that I won't skip out on is that the flybys are going to be as close as 25 kilometers. So that's about 15 miles above the surface. So it's fairly close. You know, it's not quite where, you know, your standard aircraft is flying close, because we want to avoid at all possibilities not orbiting and making an unexpected landing on Europa. We do not want to do that. So we have to stay a certain distance away. But it's really, really, really close for our instruments, which is what's so fantastic. And speaking of those instruments, here's the list of those instruments. They are kind of placed right now for what they're going to study too. So you can see the radiation. We have the mass spectrometer, the SWOCC, the magnetometer, and the particle instruments, all kind of going to be understanding what's going on in the atmosphere. Europa UVS is the UV instrument that can do atmosphere and surface, and ICE is our camera. MINES is our infrared spectrometer. ETHEMIS is the thermal imager to look for these hot spots. REASON is the radio science radar that's going to be able to ping down and hopefully get through the crust layer of ice to see exactly how deep in the water ocean is hiding. Next slide. Yeah, and so again, I talked about all these different things that we're hoping to learn about and understand. A lot of that's for the science about Europa and understanding our solar system and understanding how these moons form and what's going on these moons. But the ultimate goal, again, of NASA's Europa Clipper mission is to assess the habitability of Europa. And again, with this idea that when we go in the darkest, deepest spots on Earth's oceans where we did not expect to see any life, it turns out it's teeming with life. And partly that can be from these things called black smokers, these hydrothermal vents that actually provide the energy needed for animals and critters, water critters, to sustain at the darkest, deepest depths of our ocean. And so this schematic on the right sort of shows some possibilities of what Europa might look like. I'm inclined to say that this is probably has a lot of really good information about what we will see. But what I'm really excited about with this mission, like most NASA missions, is all the stuff that we didn't even know to expect. So, you know, we have our visions of what it might look like now, but when we get out there, there's a good chance we'll find something totally different and surprising, because that's just how space exploration always goes. Next slide. And so again, stay tuned. The mission is planned to launch in the next couple of years and arrive in the late 2020s. So it's not too far away where we'll actually get to get these images. If you guys can think about it, just imagine the geology, those features that we're going to see up close, possibly flying through a water volcano eruption. There's a lot to be excited about. So I hope you all stay tuned. And stay as interested as I am. Last slide, I think, is the next slide. And this slide should just have some information for you all. You can follow me. I have a website, tracybecker.space, and Twitter that I'll mostly post Europa Clipper stuff about. And of course, the mission is on Twitter and on Facebook and on websites, so you can learn all about the mission after this is done. And I wanted to end with a nice picture of the team. This is the science team from back in February when we met at NASA's Jet Propulsion Laboratory in California. Probably the last trip I've had, the last travel I've gone on. And of course, for those of you who are fans of sci-fi, we have a monolith And I'll leave it at that so that only the people who know what that reference is actually even knows what I'm talking about. Okay, and that's my talk. So I'm really excited to take any questions that y'all might have.
Thank you very much, Dr. Becker. We're going to give people a couple of minutes to put questions in. Thank you very much for your talk. I did have a question that came up, and I'll stall for a minute while I wait for people to add questions from them. But we talked about the mission launching in 2024 and then being out at Europa by the sort of the end of the decade. What types of science opportunities do you see for students that may be starting their academic career now that might be coming out of this mission at the time it gets to Europa?
Oh, that's a great question. Yeah, I think certainly there's lots of opportunities, right? All of these missions are sort of long duration missions. So the people that started this concept was decades ago when this concept got started. And so not only will it be 10 years-ish when we're there collecting data, we're going to collect so much data that we're not going to be able to analyze all of it in just the time of the mission. So if people are interested in the science themselves and becoming a scientist and studying Europa, that's a very real possibility between now and then. If you're a college student currently and you're interested, do internships, look for internship opportunities through your college, through the National Science Foundation has a program called an REU, Research Experience for Undergrads, that you can work at different institutes or observatories and potentially get involved in this mission or other missions or other telescopes or other research projects. So there's a lot of ways to start getting involved now, and that would kind of maybe set you up to be even part of the mission at some point, or certainly analyzing the backlog of data that will exist by the time the mission's over.
Okay, we do have a few questions coming in. First question is from Kurt Benward. He asked, are tidal forces responsible for Europa being warm enough for there to be liquid water? And any guess as to what the temperature of the water might be?
That's a great question. So the temperature of Europa's ocean, there are some estimates. So it's very cold out there, about negative 210 degrees-ish, maybe colder in certain regions. So the surface is very, very cold. I don't know exactly how cold they think that the ocean will turn out to be. I guess a little bit warmer than just what the surface is. But yes, the first part of your question is absolutely correct. So the tidal forces are what cause Europa's interior to be warm enough. It's not just the tidal forces from Jupiter. What makes it so interesting is that those 4 Galilean satellites, some of those moons are actually in resonance with one another. And so what that means is that, for example, if Io orbits around Jupiter twice, it does that in the same amount of time it takes Europa to orbit around Jupiter once. I think I have those numbers right, but the idea is that the moons will have these sort of timely lineups where they're sort of kind of on this racetrack and kind of hitting each other at the exact same points. And so usually the way that this is sort of explained is the idea of if you're pushing a child on a swing, and if you sort of just randomly put your hands out there, you're not really going to help the kid start to go high up on the swing, right? You need to time it so that every time the swing oscillates backwards, that's when you're hitting to make the swing oscillate forwards. And this is what happens with these moons that are in resonance with one another. And so the moons outside of Europa are pulling on Europa, and Jupiter, obviously interior to Europa's orbit, is pulling on Europa. And so this combination of tidal forces is really what keeps Europa's interior so warm to have the liquid ocean. Great question.
Okay. Ann Matthews asks, will NASA be able to provide real-time footage of the flyovers or recorded video when the flyovers go by?
Oh, awesome questions. So there will be multiple images being taken, but it won't be a video in the sense of what we kind of imagine a video right now, like what we're talking over right now. and by real time, I mean it'll take a little bit of time for that data to actually be sent back to Earth once it's collected. And then, but one of the cool things about NASA is that all of this data will be made available, and I'm sure any of the best images that we get will be shared with the public as soon as we can share them. But generally, the data will ultimately be public to everybody to look at some point. But it won't be. We won't have the opportunity to do kind of real time live video. Partly that's prohibitive because of just the data that it requires. So if you think about even just how much it takes to upload a video versus upload one picture, that's not really capable to do. It's not really the best use of our resources. We want to get as much high resolution data as possible, and so you want to do sort of images rather than a real time movie footage, and that's how you're going to get the best resolution as well. So it won't be real time, but we'll see a lot of cool, approach images that are taken and probably can be stitched into a really cool video showing kind of how Europa's moving. And again, if we see any kind of activity like a plume, we'll have a bunch of very short exposure images that we can stitch together to essentially like making a movie. So, but yeah, there won't be like a live stream of what's happening, unfortunately. That would be cool though.
That would be very cool, but understandably, there is a little bit of a time issue and a data processing issue to begin with.
Yes.
Another question from Andrew Greenberg from Portland State University. Who's actually building the spacecraft? He asked JPL or a subcontractor, because I know that SWOCC is responsible for some of the instrumentation, but who's building the actual bus for the spacecraft?
Yeah, so it is the Jet Propulsion Lab that's building the bus, the spacecraft itself. And then the instruments are contributed by different institutions. So I did mention Southwest Research Institute is delivering 2 of those instruments, the mass spectrometer and the ultraviolet imager. I could go through all of them maybe off the top of my head. I think I mentioned the dust collector is being built at the University of Colorado. We have instruments being built in Austin, University of Texas, University of Arizona, or Arizona State University. I always mix them up. I'm going to get in trouble for that. We have an instrument being built out in Arizona, 1 instrument being built in Colorado, 3 instruments here in Texas, and some of the instruments are being built at JPL as well. So there's multiple instruments contributed from different institutions, different people all across the US. There are international collaborators on a lot of these instruments. But yes, the JPL is leading the mission and also providing the main spacecraft itself.
We had another question. This particular one wants to remain anonymous, but can you say more about what observations the Juno probe can contribute to understanding Europa?
Yes, and I'm going to go back and just say it was ASU and not University of Arizona. Not my apologies. Yeah, so Juno is doing a fantastic job right now. That is also actually a mission led out of the Southwest Research Institute. So we're really, really proud of that spacecraft. It's trying to understand the depths of Jupiter for the most part. And so its focus is a little bit different than the focus of Europa Clipper. However, what we're really learning from it right now, which is going to be critical for Europa Clipper, is how intense is that radiation environment? So how, what are the radiation levels? How do they vary? When do they vary? Why do they vary? That kind of information is critical for our spacecraft's health and our instruments' health and our planning for the observations. And so we're learning a lot about that. And as the Juno mission is evolving with time, basically the orbit of Juno is changing, and it's actually taking it out closer to where Europa orbits. And so we're actually, as we progress in the mission, we're learning more and more about the radiation environment closer to where we really care about it, which is close to Europa, from my perspective for Europa Clipper. But Juno is learning a ton of stuff about Jupiter itself, and all of that ties together, right? One of the things we ultimately always want to know is how did our planets form? How do our moons form? How did our solar system come to be in the configuration that it's currently in? And so understanding the core and the center of Jupiter and understanding kind of its structure, interior structure, tells us more about those exact questions. And so we learn already a little bit more about Europa that way. And vice versa, as we learn more about Europa, if we can learn more about its history and how it's evolved, we can probably say more things about Jupiter complementing that Juno data set with the Europa Clipper data set. I will say there's also, really importantly, the European Space Agency is flying a mission to the Jupiter system as well in the 2030s. And so that mission is named JUICE. It's the Jupiter's Icy Moon Explorers. And that mission is going to go to Europa. It's going to pass by Europa a few times, and Ganymede and Callisto. So it's going to give us some of that comparative understanding of all of the different moons in the Jupiter system.
Sounds like a very comprehensive observing strategy, and it's a very good way to piece things together with the multiple spacecraft. We have one more question. This comes from Jake Bullard. He asked a very good question that actually came to mind for me. But what would be the next step if, say, Europa is found to have habitable conditions? Then what?
That's a really great question. First, I'll probably jump up and down a bunch. But the next steps actually after Europa Clipper, there are people leading the effort for a follow-up mission called the Europa Lander. And that currently, it's had its own funding ups and downs. But the mission itself, the concept is to land on the surface and then really do the next step. So if it's habitable, let's go find out if it's inhabited. Let's go there and see what else we can learn. And so Europa Lander would be much more of an astrobiology focused mission, landing in a specific spot. Europa Clipper will do a lot of great reconnaissance for a follow-up Europa Lander mission. And it would basically land in an ideal spot to land, but also most scientifically interesting, and probably do some sampling of the ice, and various other instruments and demonstrations on trying to better understand what Europa could potentially be inhabited by, or perhaps in the past if they can find any relics. Of course, there's also even crazier, cooler ideas out there too. I mean, Europa Lander is pretty impressive and going to be pretty amazing if that can happen. But the next steps, I think people are already talking about, submarines or somehow melting through the ice to get samples directly from the ocean. But to do that, we really need to understand how thick is that ocean. That's one of the key measurements that Europa Clipper is going to make. We can't just melt our way down, and if it's miles and miles and miles and miles deep. So I think there's a lot of imagination about what happens next. But concretely, what would I hope happen next would be the Europa Lander mission, which is a pretty well-developed concept at this point of how we would land and how we would take more measurements from the surface of Europa. Again, the difficulty being that radiation environment. So a lander can't really, it's got to withstand the radiation, and the question is, how long can it do that for? And so these missions, a lander would probably be a fairly short mission compared to Europa Clipper or any other missions that we've seen in the Jupiter system. And so that would be the challenge. But there's definitely plans for what's next. I think one thing I should mention that's really important is the idea of planetary protection. So one of the basic fundamentals of the Europa Clipper mission is we want to explore Europa, but we don't want to cause any damage to it. So if the moon does harbor life currently, or could in the future harbor life, develop life somehow, we do not want to accidentally have any negative impact on that development of life. And so we have very strict planetary protection protocols where we will, not allow the spacecraft to touch Europa, our current spacecraft at least, so that we don't accidentally deposit any little signs of Earth life that somehow can manage to stay on board and survive through space, and then potentially infect any life that's on Europa. So that's one of our sort of important roles that we have from the Europa Clipper is to make sure that if it is habitable, we're not the ones causing the destruction or causing the habitation to start from our own, you know, Earth brought life. So that's a great question.
Okay, and one final question came in, but what form of propulsion does the spacecraft use to travel, and what is the plan for the spacecraft post flyby?
Yeah, so we have solar panels that's powering the spacecraft, which is that's a pretty impressive feat, that we can actually generate enough energy using solar panels, and maintain this whole mission. So that's our primary source of energy. So again, we'll be doing at least 40 something flybys, depending on what the final tour looks like. And if the spacecraft is in good health after the nominal, like, first phase of the mission finishes, we would hope that we could then do more. So we would want to go do more flybys and maybe try to see different spots that we missed in the first set of flybys. Focus on areas that we found or identified that are really interesting, and then ultimately, when we can no longer power the spacecraft or control it anymore, when we no longer can do that, that's when we would intentionally dispose of the spacecraft again, so that we do not have any accidental chance of impacting Europa. Because if we just kind of leave it out there to do its own thing, just, you know, solar wind, other effects, radiation effects, could actually end up causing it to go on a trajectory that we didn't expect or want it to go on, and it could ultimately end up affecting Europa one day. So there's right now, it's not the whole plan. The whole tour isn't fully designed yet. There's still a lot of planning going on, but we would probably crash it either into Jupiter or potentially into one of the other moons that we don't expect to be habitable.
Okay, that's the last of the questions from the live stream. Dallas, do we have any questions from the Facebook broadcast?
No questions from here.
Okay, well, I'd like to thank everybody for watching today, and thank you, Dr. Becker, again for a great talk that was very informative, and based on the questions that we got, you clearly struck a chord with the audience. So, and I would ask all of the audience that has come in and joined us, if you like these types of physics and astronomy lectures, please feel free to support the Southwestern Community College Foundation. They do support our physics and astronomy lecture series by supplying resources for talks like these to continue. Also, follow us on our physics and engineering page at Facebook at facebook.com/SOCC all of our physics and engineering page will have more information about upcoming lectures and upcoming events, such as our Invent Oregon teams, which will start taking applications in the next week, and we'll start working through till next spring, where we'll have our showcase of the inventions that our students can come up with for the statewide competition. We have a number of NASA research projects that are ongoing. Stay tuned with that. And if you're interested in looking into NASA research and you want to get involved in the types of physics, chemistry, and other sciences that can lead to planetary science and let you be on the cutting edge of analyzing some of this data later on as it comes in, you're always welcome to join us at Southwestern for a number of classes. We have degree plans in physics and chemistry and in engineering that can help with a lot of these, that can help prepare you for doing some of the planetary science work if that is something that you're particularly interested in. And I'd once again like to thank Dr. Becker for a great talk, and thank all of you all for attending. Hope you guys enjoy the rest of your evening, and look forward to our next talk.